Honorable Sushmita Mitra from Indian Statistical Institute, Kolkata. The session will be chaired by respected Professor Dr. M.D. Atikur Rahman Ahad from Osaka University, Japan. Our whole session will be moderated by respected Professor Dr. Abdur Razak from Guinea University of Bangladesh. I would like to inform you all that we have 35 minutes for presentation and around 10 minutes for discussion. A reminder will be given 5 minutes before the presentation ends. May I now hand over the session to Honorable Professor Dr. M.D. Atikur Rahman Ahad. Thank you all.
Thank you, everyone. Welcome to the keynote session by Professor Sushmita Mitra. So now it's great to have her in this conference. Our topic is on intelligent analysis of brain images. She is a professor at the Machine Intelligence Unit, Indian Statistical Institute, Kolkata, India. We know that this is one of the best institutes in the world and of course in India. And I visited one of her co-authors. I guess her boss once as well. I mean, Shankar K. Pal. So I visited him and the office and your place. So, and I found that it's wonderful. I mean, when you enter and other things. And apart from that, I mean, she's an IEEE fellow and IAPR fellow. IAPR is International Association for Pattern Recognition. So the pattern recognition's #1 forum in the world. So to me, if someone is an IEEE fellow and IUPR fellow, then no need to introduce further. I mean, how many papers he or she has and what are the achievements? I mean, it's immaterial because being a fellow of IEEE and IUPR is unbelievable achievement. And especially from developing countries like India or Bangladesh, if someone can achieve this, this is, I mean, extremely, extremely superior. So I salute her to be with our conference and just heard that, I mean, she was a visiting professor in several universities in University of Alberta, Meiji University, Japan, Aalborg University, Denmark, a bit at different periods of times. And definitely she achieved many awards and fellowships. And she has, she authored some of the books which are available. You can visit her website and you can see that her books on neurophysiology, pattern recognition, subcomputing, data mining, bioinformatics, and especially introduction to machine learning and bioinformatics, which will be interesting for young researchers as well. And I mean, those who are very, very active in the research community, they are also active in volunteering in different forums, especially top journals and conferences. Apart from that, I mean, she's the IEEE Kolkata section, which is one of the largest sections in and active sections in India. She is the chair-elect of IEEE Kolkata section. So which means that, I mean, those who are active in the community and serving the research community, they are not only, I mean, volunteers, at the same time, they are actively top researchers. They should be actively top researchers. So those who are younger here, and we have some participants here, but at the same time, more than 150 young teachers and researchers are on site with pure social distancing. They are enjoying your talk. So I would like to request Professor Sushmita to start her presentation. Please, Professor Sushmita, and we'd like to listen from you. Thank you so much.
Thank you, Professor, for those kind words. So let me share my screen. Uh, yeah, so uh, can you see? It's okay?
Yes, Professor.
Okay, so let me start. So it is it is based mainly on the PhD work of one of my students. So I thought I'll focus on that to highlight how AI can be used in medical image processing. So its title is Intelligent Analysis of Brain Images. So what we'll be dealing with is very fast. We have to go. I think we are also delayed, and I apologize for that. And so we will first have a short some applications in machine learning, which is shallow learning, followed by some amount of deep learning that this thesis covered. So it's about brain tumor segmentation, detection, and then classification into high and low grade and survival prediction. This is some of the work that we have been undertaking here for some time. So it will involve mainly brain tumor MRIs, which are typically used in this case because of their amenability to this kind of processing of the brain and the nervous cells. And the objective is to provide improved diagnosis, prognosis, and treatment planning towards improved tumor management. So this is based on the PhD thesis of Shubhashish. So in medicine, we do have imperfect knowledge, either because of the incomplete understanding of the mechanism, some empirical issues involved, then imprecise test measurements, uncertainty of the normal ranges of the results, simultaneous presence of more than one disease condition, and often missing information. So this is a very appropriate application domain for the application of intelligent analysis, some kind of learning. And we must ensure that this is not expected to be a replacement of the medical personnel, but as an assistive tool, as assistive intelligence to help them. Because in our countries, in the developing countries, we have a huge population and comparatively fewer number of medical experts. So in such issues in the villages, in the distant villages, we need access, and the internet can be used and the imaging devices can be used such that the some kind of assistance can be provided through the computer to help them process the huge volume of data they may need to handle. And we also have some kind of interactive or active learning where insufficient ground truth or annotated information is available because of the expense involved. So this kind of learning can help there. So the first one, let's go fast into the automated detection. So multiforme is one of the deadliest kinds of brain tumor, which has very poor prognosis. And typically, you have invasive biopsies, which are, painful, and often the patient gets scared. So the objective is to use non-invasive imaging methodologies so that we can try to use them as some kind of replacement of the invasive procedures in the long run. So that is the objective of this research. And now the MR imaging has different sequences, and each of these sequences are useful for modeling different components of the tumor. It could be the blood flow or the edema region or the actual tumor and so on. So we find that each of the sequences are important. For example, you've got the four sequences T1, contrast enhanced T1, T2, and flare. And if you look here in the table, the different parts of the tumor of the brain, you've got the cerebrospinal fluid, the edema, the tumor, gray matter, white matter. Now, when you use flare, you're able to distinguish the tumor region very well. So this is the tumor region, the brightest part. The second brightest part would be the edema, but it's slightly distinguished. Whereas in T2, you find that edema and tumor come under the same contrast level. So you see here, you can outline the tumor very well, and different components give you different parts of the tumor. So that is useful when a neurologist or a neurosurgeon is confronted with the images. So we thought that all the four sequences together, as you see here, would be a very useful way to start with. So this is the marked one in color, of course, for better visualization. Now, there are two kinds of tumors in the brain, the glioma, the high grade and the low grade. Obviously, the high grade is more dangerous. And you see for the naked eye, the human naked eye, it's very difficult to distinguish between the two. So now we thought that the computerized technique with AI would be useful in this sense. So we use in the first part of the research, we employed the concept of saliency. So what is saliency? In natural scenes, you see, if you look at this image, the bird is the salient object and it immediately catches your eye. And when you compute in terms of the intensity level also, this is the salient region. And even radiologists, when they look manually at a picture, their eye also catches something which stands out to grab the attention, something out of the ordinary. So we thought we could use some of the mathematics and saliency and map it to the medical domain, because the natural scenes and the medical images do have some differences. So we thought, let's start by trying to map the saliency component. So what is saliency? Something which stands out. See, this is standing out as the color, here the orientation, here the curvature, here the texture, and maybe something local, something which is different. So this was the model. It was published in PLOS 1 in 2016. So we mapped it to the pseudo color components RGB, and then to the L star A star B star framework, and then generated the saliency map of the tumor. So in the RGB, what we did was we mapped the different combinations of this T1, T2 and flare ABC with different combinations to the different colors. And then ultimately we went to the L star A star B star. This is pseudo color. That means it's not real color, just mapping that so that you can visualize better. Now, when you map it to, if you look at this, you see that this is the color cube, the three-dimensional color cube, and we see that the edema region and the tumor region, they stand out in these two combinations, the ABC and the ACB, because the amplitude of the color components are higher in these two cases. So any of these two combinations could have been employed. However, we chose to stick with this one. Now this is the mathematics. So we first converted it into a size W by W, a square image, then computed the centers of each of the patches. We had to have patches of size K by K. Then we computed the distance between the different patches. Now we introduced the adjacent distance between adjacent patches. So what happened was, when you, in this distance, in this saliency, we introduced this part in our research. So thereby, with the assumption that neighboring regions of a salient one are also likely to be salient, such that if two regions are salient, we assume they are adjacent to each other and the distance will be less. So that ultimately the denominator lower means the value will be higher. And then we also use this principle that when an observer views a far off scene, the focus lies on the entire region or the global perspective. Whereas if you look at it from a closer distance, you focus more on the local information. So we try to superimpose all the different levels on it. And so that the superposition, like here you see this patch size 4 by 4, that means you're looking very close to it, so it has more details. Patch size 8 by 8, 16 by 16, 32 by 32. So here you see the more global information is available. This is the color coded component. So what we did was we combined all these by this kind of an equation. We are not going into the mathematical details. If you are interested, you can refer to my web page and we have the publications there. So this is just to give you an overview, and we are short of time. So finally the saliency map was like this after the computation, and we applied some kind of mean filtering and with a smoothened thing, and then the proto object was detected from there. So the detection of the seed point, kind of seed point, the proto object, around which the segmentation would next be attempted. So this was an adaptive threshold to find out the proto object. This was some experimental result of how this is the ground truth, and this was what we got. And then this was some of the quantitative results in precision recall and ROC curves. And now we also tested with disjoint multiple tumors. There also the system was able to detect properly. So this is our method, automated GROWCAT we called it, and it matched well with the ground truth. Then we extended it to the 3D saliency map. So what we did was we took the the whole lot of slices and then combine them. I don't go into the mathematical details, just to show you some pictures. So we generated the label map, the 3D proto object along the three planes, the axial, the sagittal, and the coronal views. And this is the 3D extracted tumor. This is along the axial plane, sagittal plane, and the coronal plane. So this was the quantitative evaluation of the object detected, the segmentation in terms of the dice coefficient. And also, since we did it, we studied the reliability or robustness over multiple runs, so that it was robust enough. And the coefficient of variation, CV, was used for measuring that. And this is the 3D and 2D views by our algorithm. The dice score values are given and some comparative study. This is the coefficient of variation, and it was good enough. So this is some qualitative result of different patients samples, the extracted tumor. Okay, so with the use of saliency, we were able to detect the tumor fast, localize on that, and then we need to delineate it or segment it. So using one seed point. So you see in the normal grow cut, which is the semi-automated version, you have multiple seed points. So here we are trying to find out something with the minimum user interaction, but with a fast computation time. So we use the concept of thresholding. However, we observe that Otsu thresholding, multi-level Otsu thresholding, requires order of L raised to m computational complexity. So where m is the number of classes and L is the number of gray levels. So this is very high. So this is Otsu's method. Typically, when you have binary thresholding, you have two classes. When you have multiple thresholding, then you have the multiple classes, same classes, and m minus 1 thresholds. Then the computational complexity is high. So we want to get as good a performance as Otsu, but with lower computational complexity. So we try to employ the discrete curve evolution, DCE. So this is a meta-heuristic optimization technique which is typically used in skeleton pruning. So what we did was we mapped this curve. It's a digital curve P is represented by a piecewise linear combination of the vertex. So vertex set is V1 to Vk, and they are joined by the line segments. So line segment joining the adjacent pieces of vertices. So we compute a cost F between adjacent pieces of line segments. So you see, if the cost is high, that means there is a valley or a peak, because the angle changes. It's cos theta basically. So the higher cost corresponds to peak or valley. So what we did was each of the points, each of the line segments were initially mapped the piecewise linear curve, and then we gradually merge the two line segments with minimum cost. So here is the demonstration, just a toy example. You see, these are all the points. So all the line segments, gradually they are merging. If you observe, see, they are gradually reducing based on the minimum cost. Ultimately, you have to pre-specify the number of classes you want to have, and it will converge on those 2 points, those n set of points, and that will be corresponding to the peaks or the valleys. So here it converged here. So when we compared with the multi-level Otsu, which was the red point, and the DCE detected significant points or the peaks or the valleys. So this was the difference. So what we thought was, let us now do binary Otsu on each of these uh, points. So thereby we considered the interval between each pair of thresholds, and then we applied bi-level Otsu at this stage. Now bi-level Otsu is order of L square because two classes only. So we were able to avoid order of L raised to m, and the result was very close to the multi-level OTSU with a much lower computational cost. So here is the computational complexity. So the first one order of L, and the second one bi-level OTSU for the M classes was this. So it is order of L square. Whereas applying multi-level OTSU straight away would be order of L raised to M. So this was the gain. This is the flowchart. So the initial image, you set the number of classes you want, that is M, and then you generate the intervals using DCE, then generate the local thresholds for each interval using bi-level OTSU, and generate the segmented images corresponding to each threshold. Now you select which segmented image you want to focus on and select a point within that ROI. So one point is put, one seed point, and it does some post processing using connected component analysis, the morphology operation, then hole filling, and then the extracted ROI is obtained. So we also experimented with multiple ROIs, regions of interest, and there also it performed good enough. So this was then extended to 3-dimension, whereby we were able to extract the different tumor regions, the edema, the necrosis region, and the whole tumor. So this is some pictorial views, and this is the quantitative result in terms of dyes, sensitivity, Hausdorff distance with the standard deviation marked. So for the whole tumor, the enhancing core, the necrosis, and the edema, and the Hausdorff distance. So with that, let's move on to deep learning. How much time do we have? How much time do we have?
I think you spent 16, 17 minutes only.
Okay, fine. Thank you.
So still you have, yeah.
So machine learning, so long what we did was when you do machine learning, the shallow learning, you need some kind of feature extraction. You need experts. So what is radiomics? Radiomics is the high throughput quantitative imaging parameters. So from the image, you need the imaging features. So high throughput, that means huge volume of quantitative features, which have to be designed by the human experts, which is the expensive part. And AI, as you know, is artificial intelligence. Now, radiomics is an interdisciplinary topic involving machine learning, deep learning, computer vision, and medical image processing and analysis. So, because radiomics is applied to radiographic images, which are typically used in medical imaging. So radiographic images, from that you have to extract the features. Now this is some of a brief overview of the work that we do in our lab. So we worked on X-ray images. Recently we published on COVID screening. Also it was published in SSCI 2020. IEEE SSCI. This is on diabetic retinopathy images, fundus images, early detection. This was funded by Intel, and this is about analyzing the connectivity of the deep networks, because you see deep networks, although they do perform good enough, but their only flaw is that, weakness is that you need to understand what is happening. So that is a very difficult part. Often you don't understand what is happening, and that is often not very much acceptable, particularly in medical diagnosis. A doctor will not be ready to accept a diagnosis as assistance if the understandability is not there, any justification is not there. So analysis is very important. So this was one work that we undertook 2014 in a collaboration with University of Maastricht. So what we did was we used lung CT images. So we tried to establish that the semi-automated segmentation, that means the one involving 1 or 2 seed points, and then the automated processing, was as good as the manual processing which is typically used. So we established the robustness of the method using different sets of experiments. So there we had this study, we had 56 CT 3D radiomic features, and then we used features like tumor intensity, shape, texture, and the intra-class correlation coefficient was used to test the robustness over the multiple runs. So AI, a subset of that is machine learning. Another subset of that, where the learning architecture is very deep and it involves a lot of data. and high performance computers. There you have deep learning. So, whereas in neural learning, this could be a conventional multi-layer perceptron, when you map it to the deep domain, you have such a huge network. This is the convolutional neural network, the schematic. So you see, you have a lot of architectural components, which means you need a lot of uh, data to do the training. That's why without sufficient data, it's not at all advisable to do deep learning. And in medical uh, imaging problems, this is one of the bottlenecks in countries like ours, because in the United States, for example, most universities are associated with medical centers as well as the engineering faculty and the scientific faculty, so that these doctors and engineers and scientists can interact with each other on their own data, the real data, and they don't give access to that to outsiders. Whereas in our countries, the doctors are as it is, they're burdened, overburdened with the patients, and they don't have time for research, and nor do we have such a systematic framework of universities housing medical hospitals as well as the educational institutes of the non-medical faculties. So that is a huge problem. So that's why data is a problem, and that's why the deep learning is also a problem mostly. So now in shallow learning, you need the feature extraction from experts, and you have to handcraft the features. You require considerable engineering skill and expertise. And the key advantage of deep learning lies in automatically learning to generate the features. So some of the building blocks of convolutional networks are the convolutional layers, pooling layers, fully connected layers, and some others like batch normalization, dropout, max out, mostly used for regularization. So now let's move on to some of the applications of deep learning that we did. So we participated in the Mikai challenge. So Mikai challenge, the organizers provide you with access to a large amount of data, and on that challenge data you need to process, and you need to provide your outputs, and then they evaluate based on that, and you get scores on that. So here we had two participations practically. So this is the first one. So Brat's challenge data was used, and also from TCIA. So we converted it into three kinds of networks: the patch based, slice based, and multiplanar. So the objective was to detect the tumor and classify into low and high grades. That was the problem provided by the organizers. We also compared with the VGGNet and ResNet using transfer learning. So these were the three convolutional net architectures: the patch net, the slice net, and the volume net, which were the outputs of the three planes were combined at the end. And the VGGNet and ResNet were fine-tuned after transfer learning. We used leave one patient out test for validation, and this was about the details of the training and testing and the comparative study. We found that even compared to VGGNet and ResNet, the VolumeNet trained from scratch gave better performance. This was the quantitative comparison with some of the shallow learners as well as deep learners. This was the visualization and analysis of the architecture. Quantitative evaluation in terms of the loss and accuracy curves, sensitivity, specificity, and accuracy, and the testing result on holdout dataset based on confusion matrix. So this was the last one. So here we got a good position. It was ranked among the top performing methods according to the leaderboard score. So typically segmentation, UNet is used. Now you have a contracting or downsampling path followed by a bottleneck and then expanding or upsampling path. There are skip connections in between. So what happens is, as you are contracting, the local information gets lost. So here some of that local information is passed back, so that when you are again expanding, you get some of the information and prevent them from getting lost. But still, we found that in medical imaging, around the boundary there happens to be errors when you use 3D unit like this. So this is not useful in particularly in medical imaging, because you need to cut out the whole tumor. The surgeon needs to detect the whole tumor and cut it out. If such kind of mistakes happen in the visualization, then this is not a good thing. So we tried to circumvent this issue. So what we did was we introduced a novel spatial max pooling layer, whereby the maximum locations to be subsequently used during unpooling operation were passed back through the spatial max unpooling layer. This is the thing, like this is the whole tumor, this is the tumor core, this is the enhancing tumor, and this is everything superimposed. So along the three sequences, flare, T2 and T1 contrast enhanced. So this was our model actually, the multiplanar convolutional net. So what we did was we preserved the maximum location. Here the maximum location value, this is the maximum value, and so on, so that when you come back you are having this location at least. So this was useful in getting the boundary region properly represented. So the main problem that we needed to solve was the error around the boundary and the false positive. So this is about the error around the boundary. The max locations were passed, and this was about the false positive error. So what we did was we had the three planes, the axial, sagittal and coronal, and then we used some kind of consensus function to combine them, thereby the false positive could be avoided. Another huge problem is the class imbalance. If you look at this, you find that the background region has the highest number of pixels, whereas the actual tumor has the least number of pixels, and this is a huge problem in classification, because in data imbalance it performs, I mean, if it accurately classifies the larger class, that is the background region, it would give a good high, it would give a high accuracy score, whereas this is not what is desired. Our important point is the tumor, which is the minority class. So we need to have a good classification of that minority class. So that is the problem of class imbalance, which typically happens in medical imaging, because the tumor is not the normal thing, it is rare. Most people do not have tumors, so the majority class is the normal case, whereas the
And you have
rare
5
case
minutes
is the,
left.
yes, so the rare case is the tumor. So we need to focus on that properly. So we introduce the loss functions, the generalized dice loss and the weighted log loss. So we modified the loss function. So thereby, after using that, and we used TensorFlow in Python, Intel AI Dev Cloud, because this was also some kind of funded by Intel. And so the high grade and the low grade could be distinguished properly. And this is the comparison on the leaderboard score, BRATS 2018. And this was our method, Radiomics MIU. And the red marks are the ones which gave the best performance. So you find that we were quite good as compared to the other top performers. And then the overall survival prediction. Now in the survival prediction case, we resorted to shallow learning, no more deep learning, because the data was insufficient. So the organizers provided us with three classes of survivors: the short survivors, the mid survivors and the long survivors. And since this is shallow learning, we have to provide the features. And so we use the first order gray level statistics, the geometrical features, the gray level co-occurrence matrix and the gray level run length matrix. The details are in this table. These are the features that we used, handcrafted features. And this is the segmentation accuracy score in terms of dice score, sensitivity, specificity and Hausdorff. And this is about the qualitative output of the segmentation, validation phase segmentation in terms of these quantitative measures, and this is the validation phase on the survival. So with that, this is the recapitulation. So what we did was we did the automated fast detection of tumors using saliency, then the single seed tumor delineation using DCE. Then we went on to applications of deep learning for detection and classification, and segmentation and survival prediction. So with that, I thank you for your patience and I'm ready to take your questions.
Thank you, Professor Sushmita. It's a wonderful presentation and lots of insights as well. So, in fact, I have noted down 7 different questions, but I want that participants and young researchers raise questions. So, if you have any questions, please uh, ask without any hesitation. No question is simple question. Okay, don't hesitate. So while they think, I just would like to throw a few of them. One point is that that
Yeah.
when tumor is at benign stage, it is very difficult to address. And we know that most of the developing countries, our MRI machines are older and not, latest. So what happens that the MRI cannot itself produce those results when there's a benign or early stages.
See,
So,
what a
mm,
human being cannot do, a machine cannot do. So,
yes,
natural intelligence is always better than AI. Now, why do we need AI? Because the high volume of data. So, the human being will get fatigued. In our countries, we have huge population. I mean, compared to the expert doctors, the population mostly in the villages is high. So, we have a disbalance between the experts and the patients. So, we need some kind of assistance. Now, what a human being cannot detect, you cannot expect a machine to detect.
yeah. Thank you. So another point is that good that in one of your slide you mentioned about the handcrafted features. So normally because of image and computer vision domain, we find that it's already fully defeated by deep learning because of big data and so on. So another point is that most of the developing countries they do not have GPUs to access big data at the same time. So can you give some insightful points then? The future of handcrafted features in image or medical image domain, and which domains or which areas our researchers can explore without having any GPUs. So please give us some points.
Yeah, that is definitely an issue. GPUs are very important, necessary, and data is necessary. So if you don't have data sufficient, if you don't have GPUs, I don't think it's advisable to go for deep learning. Rather, handcrafted features and machine learning is good enough. So only because deep learning, what it does, nobody knows as yet. It somehow performs, somehow does something, but you need huge amounts of data, and we don't have access to data. That is the truth. Unless you have collaboration with medical groups and they maintain a very systematic way all the data, which typically our hospitals are not able to do with the huge volume of patients. So that is of course a problem. So but then you could try to use the clouds. Sometimes in the cloud you have some processing. Yeah.
Thank you. So we have a quick questions from Dr. Ali Dewan from Canada. So Ali, can you?
Yeah, thanks, Dr. Ahad. Dr. Mitra, yeah, it's a very nice and clean presentation, I can say. I have a question related to application because at the end of the day, we want this research outcome to be used in the hospitals or by the doctors. So, in that direction, actually, what you are doing, like, do you have any collaboration with the
Yes,
hospitals?
yes, we are planning. We
And
are actually in the early stages of collaboration. So, for example, I am from Kolkata, as you know. So, in Kolkata, we've got the Tata Medical Center, the cancer hospital. Tata has also set up in Kolkata. So, we are indeed in some collaboration with the doctors there. And also regarding the eye problems, I am in collaboration with the Sankara Netralaya, which is very well known in Chennai. So there also I have some collaboration, and Google is also involved there. So I mean, so we do hope in the near future we'll have some real outputs. And also we've been in our institute, a group of scientists including me have been granted a technology innovation hub by the government of India. So we've got a lot of money, and we do hope that we'll be able to take this forward.
okay, yeah, thanks. This is excellent. And how you are convincing doctors to
You
use these
know,
algorithms?
yeah, actually,
That's-
no, I know, but these days, these young doctors, they are very professional, particularly in Tata Medical Center, I've observed, and in Shankara Netralaya. They're also interested about research, and they keep one day of their week purely devoted to research. So, I mean, doctors are also changing their views. And of course, these are high level hospitals in our city. So, I mean, the government hospitals are mostly flooded with the patients because the poor people, and this treatment is subsidized in the government hospitals. Our government offers, I mean, typically free of cost. So the people from the villages come, and these doctors are swamped, although the doctors are, I mean, having very high academic performance in their college days or academic days, but then they are swamped with these patients, and they can't do research. I mean, when do they do their research? But these private hospitals that are coming up, and they are recruiting, bringing back some of the bright minds from abroad who had gone away. So these people are more interested in research, and they know that, I mean, you need to collaborate. Actually, today nothing can be done by yourself. You need to collaborate.
Yes, thanks, Mitra. It's very interesting, yeah, and I'm
Thank
very
you.
impressed too with your work.
Thank you.
Thanks.
Any other questions? If not, okay. So I have another query. Like you mentioned about the saliency or salient features. We know that I mean saliency or salient features extraction is very, very difficult. So can you give us some kind of challenging points or core areas where researchers can explore to extract more salient features, especially in medical imaging?
No, what we did was we generated some object which could be salient based on some mathematics. So then, once you have focused on that, once you are happy that you focused on the right direction, then you can extract any features from there, any of the features which are useful. These days, the extracted features are typically in terms of texture, shape, or wavelets, or something like that. So these typical features, but you need, the problem is to focus. So the segmentation or the localization is the most important part. If that goes wrong, then everything goes wrong. If you are not able to focus on the, suppose on your face, we want to focus on the eye, and if instead of focusing on the eye, your algorithm detects the lips, then everything is wrong. So the localization and segmentation is the most important aspect. Features comes after that.
Thank you. So any other questions or comments? Do have time. If we have time, we can take.
Professor Atik, we do have another session within 8 minutes,
Okay.
so we don't
So
have.
I think that we learned a lot, and if we have more to discuss, I hope that Professor Sushmita will be very delighted to interact with us I mean, by email or in the future over Zoom and others. And I'll also knock you because I have more questions on my paper. So it would be nice to discuss and do some brainstorming. With that,
Yeah,
I would
when
like
you
to
come
thank
to
you.
Kolkata again after the corona situation goes, of
Yeah, I
course,
visited.
one day corona will go, definitely.
Yeah,
Yeah,
definitely.
we hope so.
Yeah.
Yeah, so thank you so much, Sushmita, and we are very much delighted to have you. And I would like to move the points to Professor Ajak, so to do the next points, next issues. Thank you so much.
Yeah, thank you very much. I was listening all the scholarly discussions, presentations that we have in this August evening, and we heartily extend our gratitude to Professor Sushmita Mitra. She is not only renowned scientists, engineers, professionals in this field, but also I believe a very good inspirer for our lady scientists and
Yes, sure.
engineers. So she is an inspirer. So I believe it was a very nice discussion, and we are really happy to have you amongst us. But thank you, Professor Atik Ahad, for your nice chairing. And I saw that a very learned participants attended this session, and I know that this discussion may be continued for hours together, but we do have some limited time. So thank you very much again. May I now